Welcome to Chapter 7, Part 5. In this, let me make sure the microphone is on. Yes, okay, we're good. We are going to talk about how to handle problems now that we know about sn1, sn2, e1, and e2 mechanisms. Right? Something that you might have noticed by now is that they all look somewhat the same in the beginning, right? You have a substrate that is an alkyl halide. You have a reagent, and some reagents can act as nucleophiles and bases. Sometimes you have a solvent. And from that, you have to not only be able to say which mechanism is going to be responsible, but then predict the product. So we need some sort of strategy. And one of the reasons why this is such a great textbook is Klein is very good at strategy. And so let's talk about how we're going to approach these problems. One, you need to analyze your reagent. You need to decide if it is strong, if it is weak, if it is a nucleophile, if it is a base. And there's a chart that I've sent it to your email, and it is on eCampus, and we are going to go through it here, that you need to commit to memory so that you can do number one. Once you analyze the reagent, you will identify your substrate, right? Is it primary, secondary, or tertiary? Between the reagent and the substrate, you can often figure out the mechanism. Something I'm going to add to the steps over here is look at the solvent, because sometimes you're going to need a tiebreaker after you look at the reagent and the substrate, and the solvent will help you here, if it's protic or aprotic. After you do these two or three things, you will be able to determine the mechanism, all right? And then once you determine the mechanism, you know, whether it's going to be substitution or elimination, unimolecular or bimolecular, then you're going to predict the product. And when you predict the product, you are going to keep regio and stereochemical concerns in mind, right? Are you going to have an inversion of stereochemistry? Are you going to make a Zaitsev or Hofmann elimination product? Those you have to think of right at the end. So let's start with analyzing the reagent. Now, I want to point something out. I sent you a very similar chart, but it is not the same. If you are going to spend time memorizing something, I want you to memorize what I sent you. We're going to go over it here on the right-hand side of the screen. It's very similar, but there's a couple of edits. And so I want to make sure that we are all on the same page. So for instance, when we are analyzing our reagents, we need to they're all going to fall in one of four categories. The first category, the strong base but weak nucleophile. Yes, what is listed on the slide, those are strong bases and weak nucleophiles. But the only one I'm going to ask you about is potassium tert butoxide. This is your bulky base. It is a great base, very strong, but because it's so sterically hindered, it's not a good nucleophile. It is not going to participate in a substitution reaction. It is going to eliminate. And because it is bulky, it is going to give you an E2 because it is strong, it is going to give you an E2 elimination. And because it is bulky, it's going to tend towards the Hofmann product. But just figuring out mechanisms, this is going to give you an E2 mechanism. That's the only one in that category I want you to know. Then you have the strong base and strong nucleophile category. They're strong, so they are going to go by a bimolecular mechanism. So it eliminates about half your mechanism possibilities. You'll have to use other clues to figure out between SN2 and E2. We'll talk about that in the next chart. But what identifies as a strong base and a strong nucleophile? Well, it's your hydroxide, and it is your smaller alkoxide bases like your methoxide and your ethoxide. You may see any of these written with their counter ion, right? We know KOTBU is another way you might see potassium terbutoxide written. Sodium hydroxide is often used. But remember, when you see that sodium, it's this hydroxide ion that's doing the work. All right, the metal ion is just there as the counter ion. Same if you see like potassium methoxide, right? You're just wanting that methoxide ion. All right, so we have our strong base, strong nucleophile. The next category is the, let's start that fresh, weak base, strong nucleophile. We haven't really talked about this category much. What constitutes a strong nucleophile but a weak base? Our iodide, chloride, and bromide ions are big components of this category. And think about it. They're just balls of this negative charge, a lot of electron density. So they are good nucleophiles that can be attracted to that electrophilic carbon. But they're also the conjugate base of a strong acid. So they're not good bases. They're very weak bases. So they're going to participate in substitution. Almost exclusively SN2, but there is going to be an example of sn1. And we will talk about that in a few minutes. But it's going to be a substitution. Other reagents that fall into this category are our sulfur reagents. So whether the sulfur has a charge or it is neutral, like in H2S or any other thiol, sulfur has it's in period 3, so it's a lot bigger than oxygen. It's got a lot of room for that negative charge to be stabilized, so it's not a good base, but it is still a good nucleophile. A lot of electron density on that sulfur, so it can act as a good nucleophile. And then the final category is the weak, right? It's a weak base. It's a weak nucleophile. We have talked about this a little bit. That's going to be your water and your alcohols. Typically, methanol and ethanol are what we're looking at. These will not behave like any of your other strong reagents. It will not participate in a bimolecular mechanism, so it will be sn1 or E1. You really need to commit this little chart to memory. There will be questions where I just ask you to analyze, is it a strong or weak base, strong or weak nucleophile? So that's straightforward points. And then it is also critical that you be able to identify it so you can predict product. So it's an indirect way that it will also cost points. Now, once you've done this, once you've figured out which of the 4 categories it falls into, you are going to analyze your substrate and then go to our second chart. Now, again, I have an edited version of this chart in your email on eCampus, and we're going to make it right here on the on the right side of the screen. But there are going to be edits. You want to make sure that you are getting the edits from me and not just memorizing the one off the slide. So let's make our own little chart here. So you are going to go through and you are going to determine if you have a strong base, weak nucleophile, a strong base, strong nucleophile, a weak base, strong nucleophile, or a weak base, weak nucleophile. So you're going to analyze that reagent. Then you're going to look at your substrate and determine if it's primary, secondary, or tertiary. This chart will then help you pick a mechanism. Now, let's go for the easiest sides first. If you have a strong base, weak nucleophile, that's that bulky base. it is going to go by the E2 mechanism no matter what your substrate looks like. So that's one of the easiest ones. If you can identify that bulky base, it's going to be E2. If you have a weak base, weak nucleophile, and this is a change I want to make from this chart, there's no reason to put these red X's here. It is going to be sn1, E1, and you are usually going to get a mixture of products. And the reason that I say this, yes, primary carbocation is not stable, but because of rearrangements or resonance stabilization, there are plenty of primary alkyl halides that will undergo an sn1E1 reaction. So I don't agree with this part of the chart. I want you to fill in sn1E1 on each. Now, here I want you to make a little note. It is usually a mixture of both. So I say usually because there's going to be some exceptions. So I want us to take a minute and talk about that. So let's look at an example. Let's just say one that we've seen before. We've got a little tertiary alkyl halide. We're going to use water, which is a weak base, weak nucleophile. You are going to make some of your substitution product. All right, that's my sn1 substitution product. And I'm also going to make some elimination. So both are possible products. I am going to stop here at the Zaitsev product because E1 favors Zaitsev. But you might get some Hoffman as like a minor product. So E1, Zaitsev product, sn1, we have a substitution. But what about an example like this? What about this guy if we react with water? So we have a primary alkyl halide. It can leave and make a carbocation because it's resonance stabilized. And we have a weak base, weak nucleophile. Well, we can definitely have our sn1 reaction where we replace our bromine with our hydroxide, our alcohol. But there is no E1 product possible. That's because in this particular substrate, there is no beta hydrogen. You can't make a double bond back to the ring without putting 5 bonds on carbon. So it is typically a mixture of sn1 and E1 products, but we can't turn off our critical thinking skills. If there's no beta hydrogen, well, then you can't have an elimination. So when we think about this, it is sn1 and E1 for all 3 of these options, if possible. Right? If you can't do an elimination, then that would be when the one time it's just sn1. All right, now for the weak base but strong nucleophile. Since it's strong, it wants to be a bimolecular mechanism. But we know sn2 cannot occur on tertiary alkyl halide. And so that is why sn1 is also in that column. Before we move on, let's look at an example. So let's use sodium bromide as our strong nucleophile, but a weak base. And let's take a really simple chlorobutane. All right, we have a secondary alkyl halide. We have a strong nucleophile, weak base. The bromine is going to attack and the chlorine is going to leave, right? Bimolecular reaction here. We are going to make our inverted sn2 product. If we have this scenario, where now we have a tertiary alkyl halide, and we have a strong nucleophile, weak base. The bromide ion is not going to act as a base. So you're not going to get an elimination product. But the bromine can't attack the tertiary alkyl halide. It's too sterically hindered. So you are going to lose the leaving group first. And then you are going to make that flat carbocation that now the bromine can attack. So it happens in a stepwise mechanism because there aren't any exceptions to the SN2 on a tertiary alkyl halide. So we wind up getting an sn1 product. Now, I'm not showing the stereochemistry because, one, this isn't a chiral center, but also that bromine can attack from the front or the back. And so this is how you might see an this is the only time you're going to see a unimolecular mechanism, the sn1, with a strong reagent. It's this one right here. Something I do want to note while we're talking about this, if you were to see a chiral center, and let's say, okay, let's do this one. Let's say that we had this leaving group and we were going to use water. Well, the sn1 product, you may just see the OH like this to indicate that you could have wedge or dash. You may see both drawn, both enantiomers drawn, or you may even see sometimes this little squiggle line. If you see a squiggle line, this is representing a mixture, right? It's saying there's wedge and dash. So I just want to make sure that you're familiar with it in case it comes up. Okay, so that's how you handle your strong nucleophile. Now, what if you have a strong base and a strong nucleophile, something like hydroxide? Well, if it's a tertiary alkyl halide, that's easy. Can't have SN2, so you're going to have E2. Where it gets tricky, though, is primary and secondary. And sterics can lead you more to substitution or elimination, but this is where I'm going to ask you to look at solvent. All right, so if you have a protic solvent in either of these cases, the protic solvent is going to emphasize or make the elimination more favorable. If you have an aprotic solvent, so DMSO, DMF, acetone, that is going to push us towards SN2. So that aprotic solvent will give you SN2. So any problem that I give you, if it falls into one of these two boxes here, I will also give you solvent. You will for sure have solvent to help you decide. So you can see there's some changes. This is the chart that I really want you to pay attention to. After you have decided which of these 12 boxes you fall into, then you are going to ask yourself, okay, stereochemistry concerns, regiochemistry concerns. For SN2, you would have inversion of configuration. For E2, you have Zaitsev or Hoffman, depending on the base. SN1, you get a mixture, and E1, you typically get the Zaitsev elimination product. It is going to be very important that you practice. Now, we'll do a practice problem here, but I am going to post over the next couple of days a video of me working through some of the practice problems I've posted. I definitely recommend watching it. Your homework is up for Chapter 7. You need to do that. Obviously, it's for a grade. Most of us need more practice than that. Please give yourself time to do more practice in Chapter 7. So here is an example. I'm going to skip this one because this is one I would include a solvent for you. So I don't like that as a practice problem. I'll just make one up. Let's do something like this. And I'm going to use this starting material in a couple of different practice problems. And let's just make it wedged. Here we go. All right. I'm going to use methanol. Let's use... and all right, so we have the same starting material, but 3 different reagents. So starting material is secondary for each one of these. The reagent, let's look at the first one. The first one, we have a strong base, weak nucleophile. We know that bulky base is going to lead to an E2 mechanism. Now, we have to be thoughtful about which direction it's going to eliminate. And I'll even put this as a wedge here so you know it technically can be anti-periplanar to either beta position, but we also know that the bulky base tends to go towards the Hoffman product. So if I'm asking you for the major product, which I always am, the Hoffman product is going to be the less substituted double bond. All right, so that is how you can use these steps to solve a problem. Let's go to the next one. We have a strong base, strong nucleophile, secondary alkyl halide, so it could be SN2 or E2. So now we have to go to the solvent. The solvent is a protic. That is going to push us towards substitution. If it is an SN2 mechanism, then I know I'm going to have inversion of stereochemistry. Well, I should actually do the substitution. There we go. So I'm going to get an SN2 substitution product. In the last one, I have a weak base, weak nucleophile. So I'm going to get sn1 and E1 if possible. So the substitution is going to put a hydroxide in that position. It could be wedged or dashed because I get a mixture. And then for my E1 product, I am going to get the Zaitsev product. I'm going to get the more substituted double bond. So this is just a rundown of me going through the steps, analyzing the reagent, analyzing the substrate, analyzing the solvent when needed, coming up with a mechanism, and then using that to predict the product. It takes practice. So make sure to give yourself time. There will be at least one more part. In part 6, we will cover other leaving groups. But it will be the same mechanisms. We'll still be dealing with SN1, SN2, E1, E2. All right. See you in the next part.